This lecture is in continuation to our previous lecture wherein we were discussing about defects in crystals. We discussed about vacancy defect, interstitial defect, and we also talked a little basic about Scotty defect and Frankel defect, right? Now in this video lecture we would be talking more about Scotty defect and Frankel defect, right? Now we know that Scotty is the name of the Scotty and Frankel is the name of the scientist who discovered these defects, right? Now we already said this in the previous lecture that these Scotty and Frankel defects are shown by ionic solids. When we talk about these kind of defects, vacancy defect and interstitial defect, in case of ionic solids we call them as Scotty defect and Frankel defect, right? So Scotty defect is a kind of vacancy defect where a pair of ions, right, would be pair of ions, right, that is cation and anion, since it's ionic solid, would be missing from its lattice sites, right, would be missing from its latticed site. But we have to make sure that due to these missing anion and cation, it will not affect the electrical neutrality and stoichiometry of the compound, right? We have to make sure, or in these kind of defects, electrical neutrality and stoichiometry is maintained, right? How electrical neutrality is maintained, let's see here. When particles or ions, right, positive and negative ions, would be missing from their sites, from their ideal sites, which we call as lattice sites, equal number of ions would be missing. That is, if one anion is missing, then one cation would be missing, right? So it will leave, after these missing anion pair of anions and cations, it will leave equal number of anions and cations, right? And due to these equal number of anions and cations, this electrical neutrality is maintained. Because what is electrical neutrality? When the number of cations, that is positive, is equal to the number of anions, that is negative. So positive, negative is zero, electrically neutral, right? So in these kind of defects, even after missing pair of anions and cations, we have equal number of anions and cations, that is plus and minus ions, positive and negative ions, due to which electrical neutrality of the compound is maintained. And if we talk about stoichiometry, that is the ratio of anions and cations, it will also be same, because same number of anions and cations are missing, right, from the crystal lattice, right? And these kind of defects, Scotty defects, are shown by those ionic solids that have high coordination number. And in such ionic solids that show Scotty defects, the size of anions and cations are around same, right? It's not that cation is very small and anion is big, right? So the sizes of anions are of comparable size, right? So having positive and negative ions of same size, we say, right? So let's just write some points of differences, because this is important. Many a times these point of differences have been asked, right, in the exams. So we'll write it over here. Scotty defect, Scotty defect, and let's write your Frankel defect, right? Let's first understand these. Since I said that these kind of defects, Scotty defects, are shown by ionic solids that have high coordination number, and they have ions, that is cations and anions, of around same size, right? And what about density? Since we have studied in these vacancy defects that when the ion or the particle is missing, right, from its position, right, it's missing, that will make it less denser, right? Because remember that the density of ionic solids is because the particles in solids or in crystalline solids are closely packed, are tightly packed, right? So this closeness of particles will get reduced when the particles would be missing from their sides, right? So this vacancy defect or Scotty defect will result into decrease in density, right? Example of Scotty defects would be your potassium chloride, potassium bromide, right? All these will show you Scotty defects. And if potassium chloride is showing you Scotty defect, that means the size of potassium ion and chloride ion is around same, right? And Scotty defect, we say, is a kind of vacancy defect where a pair of ions would be missing. So when the pair of ions would be missing, it will create holes at their position, right? So it will result into formation of holes, right, at the lattice sites, right? So it will generate holes. And we already talked about density, right? It will result into decrease in density, right? And electrical neutrality would be maintained. Why? Because same number of cation and ion would be missing, right, and leaving same number of anion and cation. That will maintain the electrical neutrality, and again the stoichiometry, that is the ratio of anions and cations, right? Now let's see what is a Frankel defect, right? In the previous lecture I have marked these positions, right? These are interstitial positions, right? And we studied in case of non-ionic solids, right? In case of, these are vacancy, and interstitial defect is in case of non-ionic solids, right? And these are Scotty and Frankel defect is in case of ionic solids. Right. So now interstitial defect. In interstitial defect, particles occupy the interstitial positions, we said, right? Now Frankel defect is somewhat similar to this interstitial defect, right, wherein a particle, right, or a cation, right, will leave its lattice site or its ideal position and will move into interstitial position, right? For example, this particle, say this is a cation, it will leave its position and say it will move here. This is your Frankel defect, right? So in Frankel defect, a cation would be dislocated from its position and will move into an interstitial site. So if you look at this, when this will move from its ideal position to interstitial position, it will leave a vacancy or a hole at its original ideal position, right, and will occupy the interstitial. So what is a defect? What do we call to a defect? When it will leave its ideal position, thereby creating a hole or a vacancy. This is a vacancy defect, right? This is a vacancy defect. And when a particle occupies interstitial position, we call it a interstitial defect. So Frankel defect is a combination of vacancy defect and a interstitial defect, right? So we call it it's a combination of Scotty vacancy defect, I'm sorry, so vacancy defect and interstitial defect, right? And Scotty defect is due to this Scotty defect, ions, yes, we say equal number of ions or pairs, we say, are missing, right, creating vacancies or holes, thereby creating vacancies or holes at their original position. So here Frankel defect, in case of Frankel defect also, a hole or a vacancy would be created at the original position and the particle will move into interstitial site. That is why we call it a combination of vacancy defect and a interstitial defect, right? And these kind of Scotty defects, right, would be shown by those particles that have equal positive equal size of cations and anions, right? So this would be shown by particles that have equal size of cation and anion, right? Now what about Frankel defect? Since we say that in Frankel defect an ion would be dislocated from its original position, that is why we call it a dislocation. We call it a dislocation defect also, because a particle or a cation, right? A cation would be dislocated from its original position and will move into interstitial site, right? So what about the sizes of particles, cations and anions here? The size of anion would be bigger than the size of cation in Frankel defects. Why? Because we know that these interstitial positions are small, right? So only small ions would be able to occupy these interstitial positions, right? And we know that cations are smaller than anions, right? We already know, we have done this in chemical bonding and in periodic table as well, when we studied about periodic classification, that cations are smaller because the ions from the outermost shell would be removed, since we have less electrons, so more force of attraction or more nuclear force, that will make it smaller, that will make the neutral atom smaller after it becomes a cation, right? Because when it loses electrons, it will have more high nuclear force, cations, right? So cations due to high nuclear force are small in size. Similarly, if we talk about anions, they have more electrons or more electrons in the outermost shell, so the nuclear force decreases on the outermost shell, that will make them bigger as compared to their parent atoms, right? So in case of Frankel defects is shown by those compounds that have bigger anions and smaller cations, right? Shown by compounds that have smaller cations and bigger anions, right? For example, zinc sulfide and say silver bromide or silver chloride. Mainly silver halides will show you Frankel defect because of small size of silver ion. Similarly, zinc sulfide will show you Frankel defect. Why? Because of small size of zinc ion, right? This question has been asked in exams. Why zinc sulfide will show you Frankel defect? The simple answer is because of its small size, it would be able to occupy the interstitial position. Same is with silver bromide, silver chloride, right? All silver halides. So just make sure you understand that since the particle, the cation has to occupy interstitial position, so it has to be of smaller size. That is why zinc sulfide due to smaller zinc ion and silver halides due to smaller silver ion will show Frankel defect. Now what about density? If we talk about density in case of Scotty and Frankel defect, since we said when we talked about vacancy defect, in case of vacancy defect the ions would be missing from their ideal positions, from their sites. So when particles would be missing, it will make them less denser, less closely packed, right? Because the high density of ionic solids is due to close packing of these particles. So when some particles would be missing, the close packing of particles would reduce. That will reduce the density, right? Or you can also see from this, density is equals to mass per unit volume. So if this particle is missing, that means a mass is missing. So less mass means less density. You can see it from that point of view also, right? So in Scotty defects, since equal number of anions and cations would be missing, right? So mass would be missing, right? Mass would be missing, due to which mass would be missing and volume will remain same, right? So due to the missing anions and cations, the density will decrease, right? So here we say density will decrease, right? And what about Frankel defect? In case of Frankel defect, we say that one ion, cation, will dislocate or move from its ideal position and will occupy an interstitial position. It will move from here to here, right? So in this case, density would not be affected, right? Density would not be affected because there is nothing missing, it's just dislocated, right? So density, no effect on density, density would remain the same. Density would remain same, right? In this case density will decrease, in this case density will remain the same. This is one of the point of differences, right? And in case of Frankel defects, Frankel defect would not be shown by alkali metals, alkali metal cations. Why? Because of their bigger size, right? Frankel defects would not be shown by alkali metals, right? Because the alkali metal cations, due to their large size, are unable to occupy the interstitial size. We have already discussed this. It is generally shown by cations that are smaller in size because they can occupy the interstitial positions. Now if we talk about alkali metal cations like sodium cation, right? Sodium cation, potassium cation, they would not show Frankel defect because the size of alkali metal cations is bigger such that they would not be able to occupy these small positions which are interstitial positions, right? So this would, I just mention over here, not be shown by alkali metal cations, right? Sodium cation and potassium cation. And this is again important, the defect. And one point of difference is this is shown by those compounds that are highly ionic, right? And have high coordination number. This kind of defect, the Scotty defect, would be shown by those compounds, those ionic solids that have high coordination number, right? This is shown by ionic solids having high coordination number, right? These are highly ionic solids that have high coordination number, right? Then in case of Frankel defects, these defects are generally present in ionic solids which have low coordination number, right? For example, like we said, silver chloride, silver bromide, right? All these kind of compounds, silver bromide, silver chloride, these have low coordination number, right? So Frankel defects would be shown by those solids that have low coordination number, and Scotty defects would be shown by those compounds that have high coordination number, like potassium chloride, sodium chloride, right? Those are highly ionic compounds, right? So this is again one point of difference, right, between Scotty and Frankel defect based on the coordination number, right? And the first is based on the density, right? These points have been asked many times in the exams, difference between Scotty and Frankel defect, right? And the first point of difference, we have studied that the first Scotty defect was due to when the equal pair of anions and cations would be missing from their ideal positions, right? Then that is called as Scotty defect. And Frankel defect is when the ion, right, cation, would be dislocated from its original position or its ideal position and will move into interstitial site. That is your Frankel defect, right? So these are 3 point of differences. First is based on density, and this other one is based on coordination number, right? And then what is it exactly? You can define it, like from the definition only you can have 1 point of difference, that this is a dislocation effect, right? You can explain what is it exactly. And the Scotty defect is when ions would be missing, right? And what about electrical neutrality? Electrical neutrality in case of Scotty defect is maintained because even after missing anions and cations, even after missing pair of anions and cations, the number of anions and cations would remain same, so that will maintain the electrical neutrality. And in case of these solids, Frankel defects, in case of Frankel defects, the electrical neutrality is maintained. Why? Because nothing is missing, it's just moving to some other side, right? Now one thing, we said that these defects, right, they do not only modify the properties of ionic solids, they can even add to the properties of ionic solids, right? So let's see what it can add to the property of ionic solids. If we talk about electrical conduction, right, due to the movement of these ions, right, due to the movement or the dislocation of these ions, right, or missing ions, these ionic solids will start conducting electricity, right? How? One thing we know, that when a charge moves, right, the moving charge will constitute an electric current. It is due to the moving charge that current will start flowing, right? So now here we will see how a charge is moving, right, due to these defects in the crystalline solids, right? If we talk about this Scotty defect, we said that Scotty defect will leave vacancies or holes, right? So if we have this as a vacancy, say this is a vacancy, right, say this is again a vacancy, a pair of negative and positive ion is moved. Now if we apply electric current, right, what happens is a nearby ion will move and occupy the position. When you apply electric current, right, to this ionic solid, a nearby ion, right, will move and will occupy this vacancy or a hole, which is an empty position, right? Similarly, when it will move from its position to this vacant position, it will create a vacancy or a hole here. Now to occupy this position, this ion will move, right, and occupy the position of this ion. Similarly, when this will move, right, to this position, a vacancy would be created here. To take the place of this vacancy, this ion will move here. So you will see that this hole or a vacancy is moving throughout the crystal, right? So in a way, the charges have started moving to occupy that vacant position. So movement of charge will constitute an electric current. So due to these moving charges, we have electrical conduction, right? Now let's talk about Frankel defect, right? We said that in Frankel defect, again there is a vacancy created, because it's a combination of vacancy defect and an interstitial defect. When due to Frankel defect, this ion will, say this cation, will move to this position. So it's a vacancy here, right? We have a vacancy here. When you apply electric current, this ion will move to occupy the vacancy, right? So now when this will move here, we have a vacancy here, so this will again move here. So ideally this hole or this charge is moving throughout the crystal. We have a electrical conduction due to this, right? I hope this is clear to you, right? Now there is one more thing. Due to these defects, the lattice energy decreases, right? What is lattice energy? The lattice energy is when a compound is formed, right, from cations and anions, energy known as lattice energy is released, right? Now when we say lattice energy is reduced, that means the ionic compound has become softer, right? Or what we can say is the crystal lattice will collapse, because if you remember, in Scotty defect we have studied that ions, that is cations and anions, would be missing, right? Cations and anions would be missing from their ideal positions. When cations and anions are missing, it will leave vacant spaces, right? So in a way, the crystalline lattice, right, is becoming weak, because crystalline lattice is formed due to these cations and anions only. If cations and anions would be missing, then we say that the crystalline solid or the crystalline lattice will become weak, and it would be easy for the crystalline lattice to collapse, right? So these compounds have lower lattice energy and thus lower stability, right? So the crystalline solids that have defects, they have low lattice energy and low stability because of missing particles, right? And the crystalline lattice can easily collapse because of these missing particles, right? I hope all this is clear to you. This was this lecture and the previous lecture is important, right? So just make sure you just take down all the notes and try to understand, right? And I hope all this is clear to you. Thanks.